dear students, today we'll start with this matrix method for solving a multi-degree of freedom system in vibration. Okay, uh, basically this matrix method is a widely used method to determine the natural frequency of a multi degree of freedom system. The advantage uh, of this method is that a computer program can be developed to solve the equation and the eigenvalues and eigenvectors vectors can be directly generated. Right. So we know that for a multi-degree of freedom system, the equation of motion in matrix form can be represented as mass matrix M, then X double dot plus the stiffness matrix K, then displacement matrix X is equal to 0. Let's say this is our equation 1. Okay. Now multiplying equation 1 by this inverse mass matrix will have I X double dot plus C x is equal to 0. Let's say this is our equation 2. Okay, where we can say this m multiplied by m inverse will give you the unit matrix I. Yeah, this is the uh, unit matrix we can say, and this m inverse multiplied by the stiffness matrix is a C matrix, which we call as a dynamic matrix. Okay. Now the value of m inverse can be obtained as m inverse is equal to percent by its determinant. Right now, assuming harmonic oscillation of, let's say, frequency omega, will have x, the displacement can be represented as capital X sin omega t, and therefore we'll have the oscillation x double dot can be represented as minus omega square into x. Okay, which we can also represent as minus, which we can also represent as minus of lambda x, capital X, sin omega t. Okay. Where this lambda is omega square. Okay, you can say lambda is equal to our omega square. Now, the equation 2 can be written as uh, minus lambda into the unit matrix multiplied by x, plus, sorry, here it will be capital X plus C, the dynamic matrix, into capital X is equal to 0, or we can say it is C minus lambda I, okay, into capital X is equal to 0, or we can also have lambda I minus C. Okay, this should be in the matrix form, into X is equal to 0. Let's say this is our equation 3. So we can represent in this form as well. The characteristic equation, or you can say the frequency equation, is given by lambda I minus C determinant is equal to 0. This is equation 4. Okay. Now the roots of the frequency equation, that is your lambda I, are called the eigenvalues and square root of these quantities are the system natural frequencies. Frequencies. Okay. That is omega I should be the root over of lambda I. Okay. Let's say this is equation 5. Now once the eigenvalues are obtained, these can be substituted in equation 3 to find the mode shapes called the eigenvectors actually. Okay. Now we'll take an example. Let's say we have a 3D freedom system having a spring of stiffness K1 connected with a mass. Okay. Uh, let's say mass is M, having displacement x1. Then again we have a spring having stiffness, let's say it is K, and its stiffness is also K. And the second mass is having mass M, displacement, let's say x2. Then we have a third spring 2K, okay, uh, connected with a third mass, let's say it is 2M, and its displacement is x3, you can see. Okay. Now for this 3 degree of freedom system, question is, for the 3 degree of freedom system, find the natural frequency. A simple format will start with. Huh? Now the equation of motion uh, may be written as uh, mx1 double dot plus k x1 plus k x1 minus x2 is equal to 0. Then mx2 double dot minus k of x1 minus x2 plus 2k x2 minus x3 is equal to 0. Then we have 2m x3 double dot minus 2k of x2 minus x3 is equal to 0. Let's say this is equation 1, or we can write this as mx1 double dot plus 2k x1 minus k x2 is equal to 0. Then mx2 double dot minus kx1 plus 3k x2 minus 2k x3 is equal to 0. Then 2m x3 double dot minus 2k of x2 plus 2k of x3 is equal to 0. Let's say this is set of equation 2. Now in the matrix form, if you write this, we'll have m 0 0, then 0 m 0, then 0 0 2m, the mass matrix. Okay. Then we'll have x1 double dot, x2 double dot, x3 double dot, plus we'll have the stiffness matrix 2k minus k 0, then minus k 3k minus 2k, then we have 0 minus 2k plus 2k. This is the stiffness matrix. This value is this one. This is the minus k, this one, then 0 because there is no x3 component. Then we'll have minus k, this component, then 3k is this one, and minus 2k this, then 0 because there is no x1 component here, so minus 2k this, then 2k this. And this is the stiffness matrix. Then the displacement x1 x2 x3 displacement matrix, okay, is equal to 0. Let's say this is equation 3 in matrix form. Now in simplified form you can write, let us use small m instead of capital M. We can use capital mx double dot plus k x is equal to 0. The dynamic matrix C is basically M inverse multiplied with stiffness matrix, and this M inverse we can find instead of M divided by its determinant, and we have this determinant for the mass matrix. If you calculate it will be 2mq. Okay. So the value will be in the mass matrix. You can find this as 2m square 0 0 0 2m square 0 0 0 m square. Okay. So finally you can find out the m inverse will be 1 by m 0 0 0 1 by m 0 0 0 1 by 2m. Okay. You can get this matrix in inverse matrix. Now the dynamic matrix C will be 1 by m 0 0 0 1 by m 0 0 0 1 by 2m inverse mass matrix multiplied by the stiffness matrix as 2k minus k 0, then we'll have minus k 3k minus 2k 0 minus 2k and 2k. So this will be equal to 2k by n minus k by n 0, then minus k by n 3k by n, then minus k by n 0 minus 2k by n k by n. Right? If you multiply this, you get this dynamic matrix. Now, you can write therefore the value lambda I minus c uh, will be lambda 0 0 0 lambda 0 0 0 lambda. The multiplication of lambda with the unit matrix will give you this. Then minus lab k by m minus k by m 0 minus k by m 3k by m, then minus k by m, then 0 minus 3k by m and k by m will give you this equal to 0. So from this we'll have equation lambda q minus 6 lambda square into k by m plus 8 lambda k square by m square minus kq by mq is equal to 0. Now if you solve this equation, you'll have three values. So first lambda 1 will be 0.139 k by m, lambda 2 will be 1.746 k by m, then lambda 3 will be 4.115 k by m. Now the natural frequencies, corresponding natural frequencies you can have, omega 1 will be root over of lambda 1, so it will be 0.373 root over of k by m. Omega 2 will be root over of lambda 2, that is 1.32 root over of k by m. Then omega 3 will be root over of lambda 3, that is 2.03 root over of k by m. So in this way you can find out the values of the lambda and the natural frequencies, where this lambda is basically the eigenvalues, and square root of this will give you the natural frequency. This was a simple example. So further we will solve few more problems in the forthcoming classes. Thank you.